Is TPU now obsolete? TPU has been the go-to flexible 3D printing filament option for years. It's cheap, relatively easy to print with the right printer setup, and it's extremely tough when it comes to impacts and resistance to tearing. However, there are now some new kids on the block that are threatening to take the flexible filament crown. How do these other options compare? Let's find out. This video is sponsored by PCB Way. First up, let's quickly talk about printing with flexible filaments, especially TPU. A lot of older 3D printers weren't really capable of printing with flexible filaments because they used an extruder that wasn't mounted directly above the printer's hot end, which is where the filament is melted and pushed out to create your print model. The remote extruder had to push the filament down a relatively long tube before it entered the hot end, which caused all sorts of problems with controlling how the filament was pushed out of the nozzle or extruded. Jump forward a number of years and pretty much every 3D printer you can buy has a direct drive extruder, which means it's capable of printing with flexible filaments. Another issue is that by their very nature, flexible filaments are often pretty squishy. So when the extruder gears try to grip them, they often compress, which makes it harder to grip. If you try to print too fast, you can often end up causing all sorts of headaches, with filament getting tangled around extruder gears and jamming everything up. This means that printing with flexibles often has to be done very slowly, especially if it's a particularly soft material. The softness of materials can be measured using a durometer and recorded using the Shaw hardness scale. Most TPU filaments range from about 95A all the way down to about 60A Shaw hardness, with lower numbers being softer. However, from experience, I can tell you that it's unlikely that you'll be able to print with anything lower than about 90A without making some allowances and adjustments to your printer. For instance, Bambu Labs H2D is recognised as one of the most advanced consumer-grade 3D printers available at the moment. But even this printer can't print with softer TPU without a bespoke setup, like a dramatically reduced filament path that requires some special, non-standard spool mounting options. So these are some of the challenges of printing with flexible filaments, and the reason why I've told you all of this is that all of the TPU alternatives I'm looking at here seek to alleviate at least one of those flexible filament challenges in one way or another. And if you've ever hit any of these kind of frustrations, there's actually another way. You don't have to print everything at home. PCB Way can produce flexible parts for you using professional SLS, SLA and FDM printing systems, so you don't need a TPU optimized printer setup. You can upload a wide range of 3D CAD file formats, not just STL, and get an instant free quote, and choose from materials like TPU, nylon or even metal. Each customer is assigned a dedicated sales representative, while PCB Way's engineers review your files and provide feedback or suggestions when needed. And beyond 3D printing, PCB Way also offers PCB prototyping and assembly, CNC machining, injection moulding and sheet metal fabrication, making them a complete end-to-end service for makers. Check out what they can do for you at PCBWay.com. I have quite a lot of experience printing with flexible filaments now, and there are a lot of tips for getting the most out of your printing with flexibles. If you want to see that video, then let me know in the comments, and of course, subscribe to the channel so that you see any new content I make. So, I've told you about all of the difficulties of printing with TPU. So, why would you bother? Well, TPU, or thermoplastic polyurethane to give it its full name, compared to other basic 3D printer filaments, has some fantastic qualities that have always made it one of my favourites. Because of its ability to flex, it's awesome at absorbing impacts without breaking. Compared to PLA, TPU can take between 10 and 40 times larger impacts before failing. This is also in part down to its excellent interlayer bonding. I won't go into too much detail, but TPU forms polymer chains across layers, which materials like PLA don't, so it effectively welds layers together, and failures rarely happen between layers, unlike other 3D printing materials. So what about the other options? What do they do differently? One filament that's finally becoming more widely available thanks to manufacturers like Synbotron is PEBA. PEBA stands for polyether block amide, and it has some unique qualities that should give it an edge over TPU in certain areas. Firstly, PEBA's headline trait is its reported energy return of almost 80%. What this means is that it supposedly returns almost 80% of the energy you give it instead of converting it into heat. TPU, for example, is said to return somewhere between 30 and 60% depending on the shore hardness and specific brand. Where this is most noticeable is how much it can bounce when dropped. I have a number of reels of Synbotron PEBA in both 85 and 90A, so I printed not only some flexible filament test cubes, but also some tennis balls to see if I could measure this energy return for myself. Sure enough, no pun intended, when compared to TPU, there is a significant difference to how much this material bounces. I set up the obligatory bounce test with a ruler and a hard surface, and I'll show you the results later on. Another advertised benefit of PEBA is that it maintains its bounciness at low temperatures, whereas TPU apparently doesn't. To test this, I put the TPU PEBA and my other test materials in the freezer overnight to see if I could see any difference. Again, we'll look at these results soon, and they weren't exactly what I was expecting. What the results of these tests did do was make me want to print myself a basketball out of PEBA. So I set up the multi-day print on my Bamboo Lab H2S while my testing continued. Another stated benefit of PEBA over TPU is that it has a higher creep resistance. TPU, like PLA and other 3D printing filaments, has a tendency to creep or deform over time when subjected to a constant load. To test this, I printed some small elongation tests on the Chidi Q2 that I'm testing. This allowed me to attach identical weights to each one for 24 hours to see what change there was. Then I compared before and after measurements to determine how much each one changed initially and where they returned to after another 24 hours of rest. PEBA is also claimed to be up to 20% lighter than TPU because the material itself is less dense. I weighed the test balls to confirm this, and as you can see, it was consistently 19 to 26% lighter than the TPU I used, which very much confirms the 20% claim. Another big benefit to printing with PEBA is that you can push it through your extruder a bit harder, as it can take a higher volumetric flow rate, up to 7.2 millimeters cubed per second, according to Synbotron. TPU's volumetric flow rate can range from 3 to about 6 depending on the brand and shore hardness, so the time saving will vary from about 5 all the way to 50% if you max out the print speed. This could potentially make a huge difference and almost eliminate one of flexible filament's biggest downsides. It's not all good news with PEBA though. As it effectively contains polyamide or nylon, you should really use filtration of the air around the print to prevent breathing in VOCs. Polyamide is not as bad as some other filaments like ABS, but we're learning more all the time about the health implications of printing with different filaments, and it would be best to be cautious, especially if your printer is in a living space. The nylon content also makes PEBA pretty hygroscopic, which means it absorbs moisture easily. You ideally need to keep it in an airtight dry box or filament dryer while printing, and possibly consider drying it before use too. Although it's not reported in any of the datasheets I've seen, I've heard that PEBA doesn't hold up well to UV exposure. This is not something I can easily verify here, as I live in the UK and we only see the sun for approximately 3 hours every year. It will be interesting to see some long-term testing of PEBA's UV resistance in time though. Next, let's look at, surprisingly, PLA. Well, one form of it anyway. PLA HR is a filament that was sent to me by BQ quite a while ago, but until now, I haven't done much with it. PLA is not a material known for its flexible properties, and it's actually quite brittle on its own. BQ's PLA HR is a special blend of PLA that's no doubt mixed with some other materials to improve its flexibility, and was specially developed to satisfy the 3D printed basketball craze. BQ obviously felt that this PLA blend was the best option for home printed basketballs, but spoiler alert, next to PEBA, it didn't compare very favourably when it came to the tennis ball bounce test. However, I was prepared to give it the benefit of the doubt and set up the basketball print for this one too. I can't really tell you much else about PLA HR, as there is very little information about it. As it's relatively stiff compared to TPU, it's a little less temperamental to print with, but I did still basically use standard TPU print settings with some minor tweaks, as I did with all the filaments I'm testing here. I'll go through any changes I made later. I'll also show you the results of all my testing later in the video, which included PLA HR. For now, let's just wait and see how the basketball turns out. Next up is Morflex, which is another filament from BQ. Morflex isn't technically a rival to TPU, as it's actually a form of TPU itself. What's different about Morflex is that it prints like 95A TPU, i.e. easily, but the actual print will have a much lower Shore rating, reportedly 75A, which is softer than anything I've ever been able to print on a home FDM printer. Because Morflex behaves like a stiffer material before printing, it means that you don't have to do very much at all in the way of printer setup on most machines to be able to use it. You can't run it through something like a multi-material AMS, but you can usually just put it on a standard spool mount rather than having to cobble together something to feed it directly into your print head. How BQ does this is not something they like to explain, so all I can really do is test it out for myself. Using a durometer, I tested all of the different materials, and as I'm sure you're getting bored of hearing, I'll show you what I found later on. By this time, my basketball prints were complete. Now, I used the exact same model for printing these balls, and it's actually a model optimized for the PLA HR filament from BQ, not the PEBA. However, with the way the PEBA tennis balls performed, I had high hopes that this might even bounce more than a real basketball, which would be pretty special. I should say that when removing the supports from the PEBA ball, I had a really hard time pulling them away, and whether it was due to the supports sticking too well or a print defect, there were a couple of areas where I felt it necessary to repair what looked to be some gaps in print layers using a 3D print pen, and then my new Cordless Rotary tool from Fanttik. I'll talk about this more in another video when I've had a chance to do more with it, but I'd only just received it and I found it perfect for cleaning up the mess the 3D pen left. Right. You've waited long enough, let's look at the test results. First, with my durometer, I tested what the actual Shore hardness of each printed filament was. The TPU that I used, which didn't have a stated Shore hardness on it, was between 92 and 96A. The supposedly 95A PEBA was between 91 and 95A. The supposedly 85A PEBA was between 87 and 90A. The Morflex came out a little higher than the stated 75A after printing at between 81 and 84A. And then the PLA HR, which again doesn't have a stated hardness, was between 95 and 97A. So as you can see, all pretty close to what they were supposed to be. Then I moved on to the drop tests of the tennis balls. From a height of 80 centimeters, the TPU ball bounced back to an average of 25 centimeters. That's a 31% energy recovery, which is decent for a soft material, but not particularly springy. The PEBA 90A ball bounced to 54 centimeters, giving a 68% energy recovery, and the slightly softer 85A PEBA ball came in at 51 centimeters or 64%. Both of these are clearly more responsive than TPU, but a little way short of the supposed 80% energy return. Morflex sat in between, reaching 43 centimeters, which is about 54%. PLA HR was the weakest of the group in this test, only rebounding to 29 centimeters or 36% energy recovery. I then repeated this test with all the balls after they spent the night in the freezer. TPU showed virtually no change, still bouncing to 25 centimeters. The PEBA balls actually dropped slightly to around 50 centimeters, but still maintained a good level of springiness. Morflex, on the other hand, lost a lot of performance, dropping to just 27 centimeters, a big reduction. PLA HR surprised me here, actually bouncing better when frozen, increasing to 51%, which is almost identical to the Morflex at room temperature. These freeze tests really highlight the differences in material behaviour. TPU is pretty consistent. PEBA is stable with only a small drop. Morflex becomes noticeably worse when colder, and PLA HR weirdly performs better when cold. So PEBA clearly stands out when it comes to bounce and energy return, with TPU showing its strength in stability, Morflex being interesting but less predictable, and PLA HR proving quite design sensitive. Perhaps the tennis ball design just doesn't suit the PLA HR characteristics when it's warmer, and freezing it meant that the material was able to somehow use the energy in a different way. I don't know. So let's test the basketballs that were designed to be printed with the PLA HR. As a baseline, I dropped a cheap basketball. It's not set to any specific pressure or in any way regulation, it's just an example. The air-filled basketball bounced up to 66 centimeters, which gives it an 82% energy recovery as a baseline. The PLA HR, which, let's not forget, is specifically marketed as a filament to print basketballs with, bounced to an average height of 50 centimeters, which is quite a way short of my real basketball and means it rebounded to 63% of its drop height. This is way better than the 36% the tennis ball bounced when warm, and it's even higher than the frozen ball's 51%. As I suspected, the way these filaments respond seems to be very much influenced by the design of the model and very likely the way you print with it, the temperatures you use, and the infill percentages, all of it. We need to be very careful then not to draw too many conclusions from this limited amount of testing, and a lot more experimentation is likely needed to find the best way to use these different flexible filaments. So how about the PEBA basketball? The tennis ball rebounded to 68%, so it'll be interesting to see if the different design changes that. Nope, exactly 68% again, with an average height of 54 centimeters, exactly the same as the tennis ball, and surprisingly, more than the bespoke basketball filament PLA HR. But in my experience, 3D printed basketballs just don't have the right feel when you try and play with them. They're a nice gimmick to show what 3D printing can do, but not much more than that. If you actually want to play basketball, do yourself a favour, buy a real one. So, what about the elongation test? Well, after 24 hours of hanging around, pretty much all of my test pieces had stretched. All of the samples measured 80mm overall after printing, and within 5 minutes of having 2.5 kilograms hung on them, they all extended a little to varying degrees. After 24 hours, and before I took them down, some had extended quite a bit more. After carefully removing the weights, I measured them again for an instant rebound, and then I left them all to rest for another 24 hours so that I could see where they each recovered to after being stretched. I charted the results, and whilst not dramatic, it's clear that there are some lasting effects from the stretching with some filaments. Notably, the two TPU-based materials both stretched more and then had lasting elongation after being given plenty of time to recover. Both PEBA materials returned to their original length after the test, indicating that they are more resistant to creep. There are a lot of holes you could poke in this testing method, and out of all of them, this is the one I'd like to do again with more time. One major factor that we haven't talked about is cost. A big benefit of TPU is that it's cheap. So how do these other options compare? Well, let's start with the most difficult one, PEBA. There are so few manufacturers offering PEBA at the moment, and their prices vary pretty wildly. The Synbotron PEBA that I've been testing is currently only available through a Kickstarter. I personally never advise anyone to invest in a Kickstarter, but if you do, you can secure an 800-gram reel of 95A PEBA for $49 and an 800-gram reel of 85A for $65. However, they say these prices are with a 49% discount, which would make each reel $99 and $129 respectively. That is a huge amount of money for this filament, and way more than other manufacturers are charging. A quick look on Amazon will find 800 grams for $46 and a kilogram for $60. I don't think that Synbotron will actually try and sell PEBA at $129 per 800 grams. So let's take the far more sensible price of $60 per kilogram for the 90A and $81 for the 85A, which still makes it quite expensive on the face of it. But hold on, you see, because PEBA is less dense, your 1 kilogram of filament would actually be 20% longer than the equivalent weight of TPU filament. So taking this into account, you can see that whilst more expensive, it's not quite as bad as it initially looks. The others are easy, as they both come from the same manufacturer, BQ. The Morflex is $50 per kilogram, and the PLA HR is $60 for the same weight. So, all of the alternatives are more expensive than TPU when you just consider weight, but if we do some quick sums using the density of each material, and then comparing what 350 meters of each filament costs instead of weight, we can see a different picture. TPU is still a lot less expensive, but PEBA prices don't look quite so bad. So, with a decent amount of data and a good feel for how these different flexible filaments react and perform, can we draw any conclusions? Well, each filament has its uses. TPU is cheap, very durable, doesn't return so much energy, and is potentially more UV resistant than other options like PEBA. Whilst the easy to print, less flexible versions are not really suitable for things like footwear, the softer, harder to print versions are. For example, I printed these shoes out of 90A TPU from Bamboo Lab, and well, they're not very comfortable. While the print itself is very impressive, this TPU is just too stiff. Conversely, a few months ago, BQ also sent me a pair of slippers, which I believe are made from TPU. But they clearly weren't FDM printed. Their structure makes it nearly impossible to get a durometer reading, but they seem to be somewhere around 60A. They are most likely SLS printed, as it's impossible to see any kind of layer lines. However they're made, they are very comfortable and durable. I've been wearing them outside on a concrete floor in my garage all over the summer, and there's barely any sign of wear, even if there are a few stones stuck in the bottom. You can buy these yourself from BQ, and as with everything in this video, you can find purchase links in the description. Whilst you can't print flexible shoes from 90A TPU, Morflex now gives you the option of home printing softer TPU shoes, which is exactly what I did with it. Oh, but remember, you can't 3D print Dutch shoes, as you'll just end up with clogs. The Morflex printed shoes aren't quite as comfortable as the BQ slippers that feel like you're walking on clouds, but they are a lot better than the 90A shoes. Obviously, this is the main benefit of Morflex. Whilst it did seem to bounce quite well, its main selling point seems to be in giving you softer printed parts without the headaches softer material brings. It's a good innovation, and I think it could have some other great uses in wearable prints and things like vibration damping. However, its tendency to creep could mean that there's a life to its effectiveness. Other than the very specific basketball print, I wouldn't really say that PLA HR has many other uses that another filament couldn't do better. Even a different design of ball showed that you can get it very wrong in trying to use PLA HR for bouncy things. So personally, I probably won't be buying another reel when this one runs out. PEBA is the big find of this video for me, and if you need a filament that has a good energy return and that can be printed on home FDM printers, you won't find much better than PEBA. It probably won't surprise you to know that PEBA is being used more and more in the soles of high-end running shoes, and I think it has a lot more uses in sports equipment. Whilst airless balls are a bit of a gimmick, we could very realistically see some gains with putting PEBA on the surface of things like table tennis bats, or anything else where you might want some spring back after an impact. What you won't want to do with it though is use it in anything that requires damping, like tyres, or for anything trying to eliminate vibrations. I think there'll be a lot of potential uses for PEBA that nobody's thought of yet, and I still have quite a lot of it left. If you can think of a good use for it, let me know in the comments and I might try it out. Thanks for watching, and I'll see you in the next one.